Thank you very much, Thomas and Elio, for putting together this very nice workshop and for giving me this opportunity. As Elio said, I will not be talking about what I promised to talk about. Instead, I will be telling you about a new theory that I'm proposing for alpha ruthenium chloride. And this work is unpublished, but it should basically appear on the archive tomorrow. So it's almost published. Just in case anybody in the audience is interested in the kind of things that I promised to talk about, I just want to give you sort of an elevator pitch style presentation of the ideas that I was going to talk about just with one slide, and then I'll move on to this talk about ruthenium chloride. Yeah, so what I was going to talk about is also a very interesting idea that we put out recently about the universal shear conductivity of Spinon Fermi surfaces and electron Fermi surfaces. This is the reference. And so the idea is that if you perturb the Spinon Fermi surface fluid or the Landau Fermi fluid of electrons with a transverse force, with a transverse electric field very slowly, with some finite wave vector, but very slowly, so at very low frequencies, and you compute the current in response to that transverse shear force that you're applying on the fluid. So namely, you compute the transverse conductivity of those, the transverse electrical conductivity of those states of matter in the limit in which the frequency goes to 0 at some fixed Q, you will find that the answer is completely independent of all the kinematic information of the fluid, the effective mass of the quasiparticles, their interaction. So this is a result that is true for even strongly interacting fluids. And it only knows about the shape of the geometry of their Fermi surfaces. It's a remarkable universality of the transverse conductivity. So here is a plot of the Spinon transverse conductivity and the electron transverse conductivity. Both of them approach some universal value that only knows about the Fermi radius. And generally for a Fermi surface of very weird shape, it measures sort of the local radius of curvature of the Fermi surface. And this is something that it's very hard to measure with direct electromagnetic fields, but it might be possible to measure it by detecting noise. So this prediction leads to also a universality of the noise that will control the decay rate of a spin qubit placed on top of this electronic or spin liquid. The noise will be proportional to the perimeter of the Fermi surface area. So that's what I was going to talk about, but I will not. So, but if anybody's interested, please send me an email. I'll be happy to discuss more, or in the discussion or coffee break, please ask me. So I want to start with some philosophical remarks. And I think the talk by Pierce set a very nice stage for the kind of things that I'm going to talk about. So I want to start by commenting on why is it that it's so hard to find fractionalized states of matter? Why is it that there is a drought of spin liquids, so to say? And I want to begin by contrasting the situation with another field, which is the field of quantum Hall, where the situation is quite different. So this is a trace of the Hall conductivity that was taken many years ago. And you see this remarkable zoo of states, one next to the other. Each of them is a universe of its own with different correlations that appears in these systems. It's very rich fractionalization. And there's essentially zero doubt that there is fractionalization here. Every time you see a very good plateau of the Hall conductivity with vanishing longitudinal resistivity, and this conductivity is a fractional number in units of E squared over h, you are guaranteed to have fractional quasiparticles. So I want to say that, this is mostly a comment about maybe how I feel the situation of the drought of spin liquids. I want to say that, the quantum Hall community was blessed by the robustness of this very simple probe. You only need to measure electric currents to detect the presence of fractionalization. And, this was really the engine that guided, the purification of systems to these crazy levels of purity in which you see this remarkable, sequence of states. And, this is very old. Now this is even more spectacular if you look at recent traces of this in gallium arsenide. So the robustness of these guided, materials progress in the quantum Hall community over decades to be able to reach these levels. The materials were very crappy. In the early samples, you only saw this plateau. So they are blessed by this probe. We don't have that probe. But my view is that probably there is fractionalization in a lot of places. It's just we don't have that simple probe to guide how to make the materials better and how to detect it. I think maybe we have, that drought of spin liquids, we might actually stumbled upon an oasis in the middle of this desert of spin liquids, which is alpha ruthenium chloride. And yesterday, Roser gave a very nice talk, so I'll be very brief about the basics and the general aspects of ruthenium chloride. So it's a honeycomb lattice in which each of these octahedra can be thought of as having an effective spin 1/2. And, from this pioneering work of Jakeli and Kaliulin, it was proposed that this kind of materials would be good candidates for harboring spin liquids. It turns out that the material itself, without applying any perturbation, orders into a zigzag antiferromagnet, as shown here. But once you apply an in-plane magnetic field, things start getting very interesting. And so people saw that with an in-plane field, the antiferromagnetism disappears. And there appears a window of a spin liquid-like behavior before you reach maybe what would be a paramagnetic high magnetic field state. People argued that here there might be some chiral spin liquid with some quantization of the Hall conductivity, that would have a chiral majorana mode. So this is still under debate to some extent. But more recently, something really spectacular came out, and these are basically the experiments by the Princeton group. So they are measuring thermal transport, thermal conductivities of this material within plane field. And so they did not see very clear evidence of the quantization of the thermal Hall. This is a trace of the thermal Hall as a function of in-plane field. The thermal Hall more or less changes continuously as you lower temperatures. They did not see very clear evidence of the plateau. So that's still some disagreement that needs to be resolved over the longer run. But they saw some very spectacular oscillations of the longitudinal thermal conductivity, without any sophisticated data analysis. Just in the bare data, you can see the very clearly the oscillations. Okay. And the oscillations resemble those of metals. So if you plot, let's say the position of this maxima as a function of 1/b, they follow a straight line. So the slope is essentially the Fermi surface area. This is a typical plot that you would make for a metal. Okay, so they look like metals, like having a Fermi surface with quantum oscillations, even though it's an insulating magnet. So what's going on? So, this gives a very strong motivation to propose a spin liquid with an emergent Fermi surface of neutral fermions. So in particular, it gives a very strong motivation to propose a Spinon Fermi surface state. So let me review it very briefly. And the traditional Spinon Fermi surface state can be understood nicely with a parton construction, the slave boson parton construction, in which you write down the electron as a product of boson or the closely related slave rotor construction. And by the way, this parton treatment was pioneered by Pierce several years ago. And so the idea basically is that the electron breaks into this neutral fermion, the spinon, and the spinon forms a Fermi surface, whereas the boson gaps out, it freezes. The boson that carries the charge, known also as the chargon, freezes and forms a Mott insulator. So the state is an insulator to DC charge transfer because of this freezing of the chargons. But interestingly, because of this emergent, there is an emergent gauge field, an emergent U1 gauge field that accompanies this fractionalization. And because of the presence of this emergent gauge field, when you apply a perpendicular magnetic field to the plane, I'm imagining this is living in a plane, you get some induced internal gauge field that the spinons experience. And this gives rise to quantum oscillations. This was pointed out by Motrunich some years ago, and we developed a slightly more quantitative theory of it some years ago. So could this be the state that is being seen in experiments? Could it be the Spinon Fermi surface? It's neutral. It's a system with neutral Fermi surface that displays quantum oscillations. So it's a natural candidate. Something starts being strange when you look at the experiments very carefully and consider this hypothesis. So one first indication is that the oscillations are largely independent of the field out of the plane. So here, the different symbols, the triangle and the circle, correspond to different angles of the field. And the oscillations appear to be controlled, or very visibly only controlled by the in-plane component of the field, not by the one that would naturally give rise to Landau quantization, the perpendicular component, if it was just a metal. So this is a very strong indication. Sorry, that's an indication that something weird might be happening, but you might say, maybe there is just some very weird coupling between the emergent field, so that, it's very anisotropic. So you apply an in-plane field and you get just emergent field in the out-of-plane axis. So maybe it's still just a Spinon Fermi surface, just with a strange coupling, let's say, between the emergent field and the applied field. Okay, could that be the case? Well, something really strange is seen in experiments that suggests that this is not just a plain vanilla, at least a Spinon Fermi surface state. And it's the following. So when the experimentalists put the magnetic field along the B-axis, the B-axis is this axis in the crystal, they see oscillations. So this green trace here is for the magnetic field along the B-axis. But they see zero, exactly zero, or within experimental uncertainty zero, thermal Hall effect. So somehow these spinons have a Fermi surface that has a strong magnetic field, so that you see quantum oscillations, but no Hall effect. No Hall effect, no thermal Hall effect. If it was a traditional Spinon Fermi surface state, these oscillations should come hand in hand for longitudinal Hall conductivity, for the longitudinal thermal conductivity and the transverse Hall conductivity. So what's going on? This is a very strong contradiction with the traditional Spinon Fermi surface scenario. The system displays oscillations, but no thermal Hall effect. So how is it that the system doesn't display thermal Hall effect in experiments? Well, that must be the consequence of symmetries of ruthenium chloride. In fact, when you apply the magnetic field along the B-axis, this magnetic field does not break this mirror symmetry that I'm denoting here by this dashed line. This is a symmetry of the lattice, and it's not broken by the magnetic field because the magnetic field is a pseudo vector. It's even under this mirror. This mirror would forbid the Hall effect, because clockwise maps into counterclockwise by a mirror. So if this mirror is preserved, it will explain why there is no Hall effect. But at the same time, if this was, an electronic system, if these were just electrons moving, or the traditional Spinon Fermi surface state that I just introduced, this mirror would also prohibit the emergent magnetic field because it would be odd under the mirror, both for electrons and the traditional Spinon Fermi surface. So there is a contradiction. How the presence of a mirror, allows you to explain why kappa xy is 0, but it will kill the quantum oscillations, whereas experiments are seeing quantum oscillations and no kappa xy. So here is that's the motivation for what I'm proposing. Okay, so I'm proposing a different kind of a Spinon Fermi surface state that I will call the pseudoscalar Spinon Fermi surface state. And it's a different state than the traditional Spinon Fermi surface state, but it's still a state in which there is an spinon with a gapless Fermi surface. And the key difference is that crystalline symmetries act on these spinons as particle Hall conjugation. So this mirror, let's say at some site R, maps the spinon particle to the mirror side, but not the particle, the Hall. It adds a particle Hall conjugation. So the spinon number, the spinon charge is odd. That's why the name pseudoscalar. Unlike the electron charge, if it was usual electrodynamics, the charge would be even, but the charge is odd under the mirror. And then the magnetic field associated with these spinons, if there is an emergent U1 gauge field associated with this fractionalization, would have to be even. There is some similarity that one can actually work this out, that this is similar to what happens with Jordan-Wigner fermions, but I will not go into details because of the time constraints. But if anybody is interested, I can explain why this is natural transformations for Jordan-Wigner fermions. So these spinons are not very unusual. I want to say Jordan-Wigner fermions actually are a toy model of these spinons at some level. So, but how is it that then they can have a magnetic field and zero Hall effect? Well, when you go to the momentum space, because you're doing a particle Hall conjugation combined with a space symmetry, what happens is that what you will typically encounter is that these spinons are such that if you have a particle-like pocket at some region in momentum space, it will map under the symmetry into a Hall-like pocket. So what I'm proposing is that this system contains particle-like spinon pockets and Hall-like spinon pockets that are related by symmetry and with exact same size, so they are compensated. And so when you apply when the experimentalists apply the magnetic field in plane in this direction, there is an emergent magnetic field that the spinons experience out of a plane, but there's gonna be a compensated amount of particle-like spinons executing cyclotron motion, let's say clockwise, and Hall-like spinons executing counterclockwise motion, so that there will be an exact cancellation of the Hall effect because of this particle Hall symmetry. But because of the Landau quantization of this induced by this magnetic field, there will be still oscillations of the spinon density states near the chemical potential. So you will see quantum oscillations, even though you see zero quantum Hall effect. So this is the essential picture. Okay. And what I just gave you was, the essential kind of idea, the big picture idea. So let me now give you a more precise version of this idea of how to construct this idea more precisely is using the fermionic parton representation of spins, which is something that Pierce briefly also introduced in his talk. So, we can decompose the spins at each side into fermions. And this is a parton decomposition. So something that Pierce was also emphasizing, these fermions are not physical. The only thing living in the Hilbert space is really these spins. So only the states in which there is one fermion per side are physical, okay? And, for any trial state that you cook up for these fermions, the physical state is obtained after some Gatzwiller projection. So there's some operator that projects out this unphysical part of the states if you cook up some trial state for the spinons. Now, it is extremely hard to do control calculations for this physical state, keeping the full Gatzwiller projector. It's extremely hard. If anybody knows how to do this efficiently, I would be very, very interested to talk to you, but it's extremely hard. What most people do is some approximation to this projection, or they ignore it. So I will not do that. So I will not give you good reasons why this is a good energetic ground state for ruthenium chloride yet. I wish I had them. I don't have them. It's extremely hard to do control calculations of a physical state. But what you can do is very precise arguments of the symmetry properties of a physical state by knowing what is the trial state of a spin. So that's what I will do. I will not tell you why it's energetically favorable, but I will tell you exactly how to construct physical states that have these transformation laws that I presented, okay? So it's one important notion in this construction, which is the parton gauge group, okay? So there is certain unitary operations that leave these spins invariant, these spin operators invariant, but they act non-trivially on the fermions. But because they leave the spins, which are the physical entities, invariant, they are not symmetries. They are not physical symmetries. They are gauge transformations. They are not physical transformations, only gauge transformations of the fermions. And the set of all those transformations is called the parton gauge group, okay?
Inti, 4 minutes plus questions.
Can you say that again? 5 minutes?
4 more minutes plus questions.
Very good. So let's consider this mirror symmetry, M, okay? What I was able to show, and I will go quickly because I'm a bit short on time, is that in this fermion parton representation of spins, you can represent this mirror in two physically equivalent ways. So in the sense that they give rise to the same transformations of a physical spins, but they act differently on the fermions. Okay. One is an electron-like implementation of the mirror. So it does what it would do to electrons. These are what I would call normal or traditional spinons. There's another implementation of the symmetry that I call pseudoscalar, in which the spinon is particle Hall conjugated. Okay, and both give rise to the same action on the physical spins. Because they give rise to the same action on the physical spins, and because the square of the mirror operation on the physical spins equals the identity, their product must be an element of the parton gauge group. Namely, it's an operation that, you know, does this nothing to the physical spins, but acts non-trivially on the fermions. And this is that product. The product is a gauge particle Hall conjugation. So from this, it follows that for any physical symmetry that you give me, there is two representations, one electron-like and one pseudoscalar-like. And they differ by the action of an element of the gauge group. So if you wish, these two representations belong to two distinct projective symmetry groups of the same physical symmetry, in the sense of projective symmetry groups introduced in this seminal work by Xiaogan Wen. So these are two projective symmetry representations of this mirror, but they give rise to physically distinct states. There is a scalar or traditional spinon Fermi surface, and there is a pseudoscalar spinon Fermi surface. And because I'm short on time, I'll be brief here. So you can explicitly construct the trial states for these states in the presence of an emergent magnetic field, okay? And convince yourself that the physical state, the one after you do the Gatzwiller projection, the emergent magnetic field has different transformation laws. So for this mirror that acts like as it does in electron, odd, and for the new mirror, the one that particle Hall conjugates the spinon, the magnetic field is even, the emergent magnetic field. So that's the bottom line. You can have a mirror invariant magnetic field in this system. And that might be what is going on in ruthenium chloride. So here is, you know, a detailed discussion of symmetry of ruthenium chloride. Ruthenium chloride has a bunch of symmetries, even an almost exact rotor reflection symmetry by 60 degrees. There is some bond that is a little bit contracted, but it's just very weak. So one can construct, you know, states that satisfy these symmetries, these new implementations of symmetries, pseudoscalar implementation of symmetries with all the symmetries of alpha ruthenium chloride. I had some example. It's not, I don't have a very good argument for why it's energetically favorable. At the moment, I'm just going to show you a state that satisfies the symmetry, and I tweak the parameters a little bit to match the phenomenology that I believe to be relevant in alpha ruthenium chloride. So this is a typical dispersion that follows for those states. This is when you enforce the full symmetry, and this is when you enforce just the symmetry of the magnetic field being along the b-axis. So there's some pockets, some elliptical particle-like and hole-like pockets of spinons, in this case at the endpoints. The endpoints are connected by the wave vector that is associated with the formation of the antiferromagnet. So if you condense a spinon particle hole pair with this scattering wave vector, you will get the antiferromagnetic zigzag state. So this gives a very natural explanation to the antiferromagnetic zigzag state. You can make predictions with this, even if it's not completely, settled what the state is. For example, I have some prediction for what would be the oscillations of the magnetization. You should see very interesting magnetization oscillations with in-plane field of the in-plane magnetization of the system. Okay, quantum oscillations. There is very subtle phenomena associated with what happens to these spin liquids at very low energies. I will not go into details, but let me just say that because this particle hole symmetry forbids the Chern-Simons coupling for the emergent gauge fields after the spinons form Landau levels. If you integrate them out and you compute the effective action for the gauge field, you will see it doesn't have Chern-Simons coupling, even though there is Landau levels. So that means that these spin liquids will not give rise to chiral spin liquids at low energies. So once you Landau quantize the spinons, they are a bit more susceptible to confinement than usual Spinon Fermi surface. So that might give rise to a very low temperature, very low energies, the state actually forming a broken symmetry state in the presence of the Landau quantization, and maybe even a chiral spin liquid in the presence of, if it breaks symmetry. So just to summarize, that's the essence. The experiment sees oscillations of kappa xy, but no thermal Hall effect. And that suggests that what is going on is that there is a new type of Spinon Fermi surface in which symmetries act very differently than what they would in electrons or in the traditional Spinon Fermi surface picture that has a compensated Spinon particle and hole pockets. And in spite of having a zero hole conductivity enforced by symmetry, there is quantum oscillations of the density of states, and probably it's possible that the spinon pockets are located at these endpoints, the brilliance on that to connect them to the formation of the antiferromagnet. So with that, let me thank you for your attention.